Hello everyone, my name is Roger Fari and I would like to welcome you to another video. In this video we're going to continue learning about k-means. In the previous video we learned about what k-means is, its weaknesses, its strength, how we go about setting k, and many different things around this algorithm of clustering. In this video we're going to simply learn about how we would do k-means in R. Alright, let's look at the slides. So the outline of this video is very simple. Of course, we're going to have a very short recap of clusterings and k-means. And after that, we're going to see an example and cluster it using R. That's basically it. So clustering, as we discussed, is a data mining algorithm or data mining task that goes about finding the inherent patterns in the data without having a dependent attributes or without having a goal of achieving something from the data. So what clustering does basically looks at all of the attributes inputted to the algorithm, try to find groups, meaningful groups among the data objects that the members of the groups are very similar to one another and the members that are not in the same groups are very different from one another. So that's basically what clustering is. And we did see that k-means has a very simple loop that in a heuristic and random way go about finding these clusters or groups of data objects. So in this video we're going to use the the data sets of happiness indices from the World Health Organization for 2019 as we have it here. You can see it in the this slide. We have these 9 attributes, right, that we want to use to compare these, to cluster these data objects. So we've got 122. Alright, so let's look at how we would go about doing this task in R. Alright, so here we are in the R environment. So before we start anything, don't forget to set your working directory to the directory that you have this file saved at. So once you do that, you're ready to go. And of course we're going to use the cluster package, and we're not actually going to use bbmisc. So I can go ahead and remove these. Alright, so this is the only package we're going to be using. So, and once everything is ready, which seems to be ready now, we simply go ahead and run this file, which is going to read the file, and this is our data frame. You can look at it and we see that it has all these happiness indices, but at the same time the column name, which is the name of the countries, are also here. And that's better to set the index of these data object or rows as names. So the way we do that, first of all, let's go ahead and change that df to a data frame. That's actually not necessary because read CSV makes that into a df. So I'm just going to remove this, but if you had used read underscore Excel, we would have to do this before we can use row names. Alright, so let me remove this because it's not necessary now. So we switch the row names for df, and then after that we don't forget to scale our data objects because we need to standardize the data for the clustering to make sure that the scale of the attributes are not a factor. Basically we are equalizing the scale of these attributes, so every attribute have the same weight in the formation of the clusters. So we do that, and we've got all of these x's, and these are, you can see that have the index as the name of the country, and at the same time all of these attributes are between, it's between roughly between -3 and 3. So this is where the clustering actually starts after the standardization. All you need to do is to use the function PAM, which comes from this package, and you pass the data you want to use for clustering, and you set k as 3. And that's all there is to it. So once you run this, You've got your clusters. You can run this as k output, which is the output of this cluster. It gives you some output, but it sort of gives you what each country is a part of what cluster. So we've got 3 clusters here. It also gives you the medoids of these 3 clusters and their values. So these are the medoids, and these are what each group, what each country is a part of which cluster. We can also actually do summary of the k outputs, which not only gives us what country is a part of what cluster, it also gives us the silhouette scores of all of the data objects, and also the average silhouette score for each cluster, and also the total average silhouette score. So the silhouette score is something that we will discuss in the future videos. Basically, for now, look at it as a goodness of clustering. And the higher the silhouette score, the better the quality of your clustering. So, I mean, this is something you have to compare with other clusterings to see sort of which one is better. But silhouette score can be negative from negative to all the way to 1, and the higher the silhouette score, the better. So that's one thing that the summary gives us, but also the summary gives us the cluster. You see, let me scroll up here. We got what country, each country's cluster, and the closest neighbor to that country, and also the silhouette score of that specific country. So we will learn about this, that each data object has a silhouette score, and when we calculate the silhouette score for the clustering, we basically average all of the silhouette score for all of the data objects, something that we will learn. Then the summary, we also get a few other things. We get the size of each cluster, right? You can see that there are 38 data objects in cluster 1, 63 data objects in cluster 2, and 21 data objects in cluster 3. And also we get the maximum distance between all of the data objects, the average distance, the diameter of the cluster, and also the separation coefficient. And these are something that could be used when you have possible other clusterings, but without something to compare with, these values are largely just good to have, but they are not serving any purpose. But this size is very very informative. We do actually know how many data objects are in each cluster. Another thing that is important, we already see, the summary doesn't give it to us when we print the k output itself. It gives us, it's the medoid of each cluster. We can see that the medoid for cluster 1 is Burkina Faso, the medoid for cluster 2 is Dominican Republic, and the medoid for cluster 3 is Australia, which is useful for centered analysis. So we can see, okay, Australia is the representative of cluster 3. And we can, the last thing we're going to learn is the plots that R gives us. So if I run this, the plots are going to be ready by clicking enter here. I get the first plot here, which is basically the principal components 1 and 2 of the data, and we can see the labels of, we can see the clusters in the principal component 1 and 2. So we've seen principal component analysis, and PAM uses PCA to have a higher dimensional visualization of the whole data set, and we can see that only 68% or around 69% of all of the data are presented in this visual, right? So we can see how well the clustering have been able to separate these data objects from one another. If we click another enter here, it gives us the visualization of the silhouette plot, which is good to see it, but it doesn't give us any analytics value. But the previous visual was showing us how separated the clusters were that were useful to look at. One last thing we want to experiment here is that if you remember when we were doing when we were using the same data set for hierarchical clustering, when we used the words method, we saw that there were roughly 7 clusters. So let me go ahead and put k as 7 and see what happens, right? So it's as simple as that. Now I can experiment with k equals 7. And I can, see that the silhouette score actually dropped. So perhaps, this is not good, but at the same time we discussed, there is a tendency to improve the metrics for quality of clustering when we have higher number of clusters. But at the same time, we can take a look at the this visual, which is shows us the clusters, and we do see that while there are some overlap, but there are also good separation between these data objects. So this might be that K is a better clustering, and it depends on the work we are going to use this clustering result. Another experimentation I want us to do is to see if K-means is actually random here. So let me run this a few times. So remember this number, right? 0.02097895. If I run this multiple times, we would expect this number to change. Let's see if it's actually a random output. 0.029789. Let me do it again. This seems to be the same number. Let me do it again. One more time for size. We see every time we run this k-means, even though we know that k-means works in a random way, this package, this module seems to not to be random procedure. So I haven't looked into it, but I have 2 possible guesses. One is that this algorithm uses a very simple starting point. For example, you've got k as 7. The first 7 in the list is going to be used as the first centroids, or it has a heuristic to sort of start off the algorithm with a possibly good starting point in a heuristic way, but it is consistent. So like I said, even though we are learning what is the k-means in the literature, which is a random algorithm, whoever or whatever group that has created this module or this function have taken another route in the creation of k-means, and they have made some decision that the algorithm is not random. All right, until the next video.